So in this video, we're going to be looking at the formation of complex ions, what they're actually made up of, and how we can actually draw the structures of them as well. Now, starting off, of course, we've already come across our transition metals, and we know our transition metal is a D block element that has a partially filled D subshell when it forms a stable ion. Now, the thing is, when we actually form most of our transition metal ions, we normally end up with a 2+ charge for our actual ions, and we actually lose the 2 electrons from the 4s subshell. Now, of course, that along with having an incomplete D subshell would mean that of course we can form dative covalent bonds from another species, like of course another molecule or an ion itself, which we normally call a ligand, and that ligand is going to donate electrons to the actual transition metal ion, making a complex overall. Now of course, when we look at our complex ions, we need to be able to define it in the exam, and we say that a complex ion is an ion which is bonded to or surrounded by ligands itself. Now if you were to define what a ligand is going to be, we say that it is a species that donates an electron pair to a metal ion and forms a dative covalent bond or a coordinate bond with the metal ion itself. Now if you were to think back to module 2, remember what dative covalent bond is. It's a shared pair of electrons where both electrons come from the same atom, and what we're basically saying is we've got an incomplete D subshell, missing electrons from our S subshell, our 4s subshell, and so we can actually satisfy that. We can accept electrons, we can form dative covalent bonds from these ligands to our actual transition metal ions itself as well. Now you need to be able to define the 2 main types of ligands that you can get. One of them is of course going to be a monodentate ligand. When you hear the word mono, think of course one. This donates 1 lone pair of electrons to the central metal ion, forming 1 dative covalent bond to the actual metal ion itself. So basically you're forming 1 dative covalent bond from 1 lot of ligands. If you were to look at a bidentate ligand, think bi, think 2. This donates 2 lone pairs of electrons to the central metal ion, forming 2 dative covalent bonds to the actual metal ion itself. Again, you can use the word coordinate bond instead, but you've got to think about it like this, right? A ligand, let's say you've got one example over here, a monodentate ligand is going to have 1 lone pair and it donates that to form of course 1 dative covalent bond. Now if you were to look at a bidentate ligand, of course that's going to have 2 lone pairs on the same ligand, and so you can end up forming 2 dative covalent bonds itself, 2 coordinate bonds. Now I've got 3 examples over here of my actual complexes, and you can see in the first one I've got some cyanide ligands over here, and they're actually donating the pair of electrons. We don't actually need to show an arrow for a dative covalent bond in module 5 in this case, just because it can get quite confusing with the wedged and dash bonds. You can see my central metal ion is going to be iron in this case. If you were to look at the next one, right, you've got cobalt over here and you've got a tetrahedral shape. You've got 4 actual ligands, chloride ligands in this case, and of course they're donating a pair of electrons to form a dative covalent bond. Look at the next one, you've got a more complicated kind of complex over here. Again, you've got cobalt over here, but this time you've got a bidentate ligand here, bidentate ligand there, and a bidentate ligand there. You can see that one species is donating 2 pairs of electrons, 2 lone pairs of electrons to that metal ion itself as well. Now in terms of our ligands, we need to be aware of some examples. The monodentate ligands, they can either be neutral like ammonia and water, where they don't contribute to the overall charge of the complex ion, or they could actually be charged, where you end up with chloride, hydroxide, cyanide and thiocyanide as well. 4 more examples you need to be aware of. These are charged, and of course they're negatively charged. When you add them on, they end up decreasing the charge, making it more negative itself. Now in terms of my actual bidentate ligands over here, you can see of course I've got 2 examples that I need to be able to remember. One of them is going to be ethane 1,2-diamine, which I've got the structural formula for. There's carbon 1, there's carbon 2. The skeletal formula looks something like this, where I've got ethane, and then I've got 1 amine over here, and then I've got another amine over here itself as well. And what you can see is of course the skeletal formula, I've got 2 nitrogens, and this nitrogen actually has a lone pair of electron there and a lone pair of electrons there as well, and that can form 2 dative covalent bonds itself. If you were to look at the normal displayed formula, you've got carbon bonded to carbon, and then you've got hydrogens up and down, and then again over here and over here, but then remember you've got an N and then bonded to a hydrogen and then a hydrogen here. Remember, in terms of the octet rule, you've got a lone pair on this nitrogen here, And then of course on this nitrogen over here itself, this is what we call an amine, and in fact we've got two amine groups on there. So yeah, there's a skeletal formula you need to remember. Now one more thing to mention is that of course this is not going to be charged, it's going to be neutral, so it doesn't actually have any contribution to the overall charge of the actual complex itself. So I'm going to say that is going to be neutral itself. If I were to look at C2O42 minus, otherwise known as ethane dioate or oxalate, that's basically come from me having ethane dioic acid, which is just ethane with two carboxylic acid functional groups on there. I end up with something that looks like this, but of course we get rid of the hydrogens to make the bidentate ligand that we're interested in, and what we are left with is of course a ethane dioate ion, an oxalate ion itself, which is a carboxylate ion. If you were to look at this, the charge of the ligand is going to be -2 overall. It's not going to be neutral anymore. So however many lots of this we actually get on our actual complex, we end up adding a -2 on the overall charge itself. Yeah, and that's a bidentate ligand because again, this oxalate has a lone pair there, and it also has a lone pair there, and there is our C2O42 minus ethane dioate or oxalate ligand itself as well. Both examples we need to be able to remember. So moving on then, if we were to look at the shapes that we can actually get with our complex ions, this is to do with the coordination number. So basically, however many dative covalent bonds I have between the ligands and the central metal ion, that is going to determine my actual shape itself. So let's say if I were to look at exam definition, I would need to tell the examiner that it is the total number of dative covalent bonds between the ligands and the central metal ion itself. And if we were to look at the first example, if we have a coordination number of 6, try and think about it as 6 bonded pairs, 0 lone pairs, I would have an octahedral shape. Now, how do I actually draw this out? Well, the first thing that I need to be able to recognize is that my central metal ion in this case is going to be, of course, iron. In this case, on here on the right, I've got cobalt. In terms of the ligands on the left, I've got, of course, cyanide ligands, which look like this. It has a negative charge, and the lone pair is actually going to be on the carbon atom itself. If I were to look at the right-hand side, I've got, of course, my ethane 1,2-diamine ligands, which, of course, we already know it looks something like this. And, of course, I've got NH2 there, and then NH2 there itself. I've got a bidentate ligand. In both of these cases, I'm still forming 6 dative covalent bonds to the metal ion, and so I end up with a coordination number of 6. Even though one of them is going to be, of course, monodentate, where I end up with 6 lots. The other one is going to be bidentate. I end up with 3 lots. But, of course, 3 times 2 lots of dative covalent bonds is 6 itself, so we end up with an octahedral shape. Now, how do I actually draw this out? Well, the first thing that I like to do is, of course, take my central metal ion, and then I like to put in my bonds for an octahedral shape. I don't like to actually put in my molecules or my ions to begin with. I don't like to draw out my ligands. And of course, I'm going to add in my dashed bonds now, going away from me. My wedged bonds coming towards me. And then now I'm going to add in my actual ligands itself. Now, to actually attach the ligands on, we need to think about where the lone pair actually is. It's on this carbon atom. And so, of course, we're not drawing any arrows or anything for dative covalent bonds here. I'm just going to draw the line going towards the actual carbon itself, because that is where the lone pair is being donated from. The same thing over here, same thing here, same thing over there, same thing here, and then same thing here. You'll notice that I've just flipped it just because I want to make sure the carbon's bonding to iron, not the nitrogen. I end up with my square brackets, which is going to look like this to show I've got complex, and then of course I end up with a 3 minus charge itself, and there's the first one done. Look at the next one. I've got bidentate ligands here, which is a bit trickier, but we follow the method that we did before. So I'm going to end up with, of course, cobalt in the middle this time, because that's our central metal ion, and I'm going to join my wedged and dashed bonds, my straight line bonds, and so on. and I end up with something that looks like this. Now, of course, we already noticed the nitrogens that form the dative covalent bonds. We don't put any lone pairs on our actual complex ion itself. We ignore that, and we just show the nitrogen atoms here. Now, in this case, you can see that I'm actually just drawing my nitrogen atoms on to make sure that my dative covalent bond is coming from the actual nitrogen atoms itself and nothing else, because a lot of people make mistakes here. Now, the next thing is I'm going to draw out the rest of my structure. So I'm going to make sure I've got my carbon bonded over here to this nitrogen and then connecting as a bridge to the other nitrogen itself. I'm going to do the same thing over here and then go into that nitrogen there. Same thing over here, go into this nitrogen there as well. Now, the next thing to do is, of course, include my 2 hydrogens that are going to be, of course, on my actual nitrogen. So I'm going to have H2 over here like this, H2 over here like this, H2 over here like this. Just make sure it's not bonded to the actual carbon or the cobalt itself as well, and you end up with a structure that looks like this. Now, these are quite difficult to draw, so I always suggest that you use a pencil. I'm going to move mine over to the left a bit and make it a bit smaller. The reason why is because I need to put some square brackets on there as well. Regardless if it's going to be charged overall or not, we need square brackets. In this case, I've got a 3+ charge, so I'm going to show the examiner it's 3+ charge by putting that on the top right hand corner itself. And of course, there's our next type of complex done as well. So of course, there's our shape, which is octahedral for a coordination number of 6. What about if we were to have a coordination number of 4? Well, we can end up with 2 shapes in this case. One of them is going to be square planar, one of them is going to be tetrahedral. Now, in every case, if we were to have a coordination number of 4, our shape itself of our complex is going to be, of course, square planar. But the thing is, if we were to have 4 larger ligands, let's say chloride, bromide, or iodide, we would normally end up with a tetrahedral shape as well. So any big bulky ligands, they're going to be, of course, causing our shape to turn into a tetrahedral shape. How do I actually draw the first one then, a square planar shape? Well, of course, my central metal ion in this case is going to be neon. And thinking back to our previous example, remember how we drew an octahedral shape? It's going to be the same way that we draw it. Of course, we've got a flat square base shape. I'm just going to draw, of course, all of my wedged and dashed bonds, but this time I'm not going to draw my straight line bonds. So it's the same thing again. I end up with my wedged and dashed bonds drawn like this. There's my dashed bonds done, my wedged bonds over here. And then, of course, I'm going to draw my ligands. In this case, it's going to be cyanide itself. So I end up with CN, CN, CN reverse, and then CN reverse over here. Some square brackets. And then I end up with, of course, a 2- charge. The next one, tetrahedral, you've seen this one before in module 2. Copper chloride, which is going to be 2-. I've got here chloride ligands, and I'm going to end up with copper, chlorine upwards, chlorine here in the same plane, a chlorine coming towards us, and then of course a chlorine going away from us itself as well. I end up with some square brackets, which looks like this, and then I would say, of course, the charge overall is 2- here as well. And there's our 2 examples there done too. So moving on then, I've got a task for you to do. Feel free to pause the video and have a go at the following task. Resume once you're ready to move on. So yeah, looking at the formula of the ligand, I like to just chop it over here. I've got cyanide over here. It's going to be Cn-, and that's nice and easy. There's the first part done. If we were to look at the ligand, is it monodentate, bidentate? Well, we've got to remember this one. It forms one dative covalent bond. That's a key hint. So we can see, of course, it's going to be monodentate itself. So we end up with the ligand being monodentate. If we were to look at the next one, the formula of the central metal ion, well, if we were to look at, the atom, it's iron. If we were to look at the actual charge, overall it's 3- for all of these 6 lots of cyanide. But then, of course, we also know we've got an overall oxidation state, overall charge being 3-. How do I get from 6- to 3-? Well, it's just going to be +3 itself. So we end up with iron 3+. The coordination number, I've got 1, 2, 3, 4, 5, 6 dative covalent bonds. It's going to be 6. The formula and the name of the shape of the complex ion, well, of course, the formula would be iron. And then, of course, I've got 6 lots of cyanide. So the 6 goes outside the brackets. And then I end up with 3- overall itself. And the shape, we know for a coordination number of 6 is going to be octahedral itself. There's that first one done. Feel free to pause the video again and have a go at the following. Resume once you're ready to go over the answers. So yeah, again, over here, we've got the ligand. we chop it, we end up with cyanide. That's nice and easy. What type of ligand is it? Well, we know it's the same as the last one. It's just going to be monodentate, so we end up, of course, forming one dative covalent bond. The formula of the central metal ion, of course, it's going to be 2 minus overall, but of course we know we've got 4 lots of cyanide, so that's 4 minus. What's the difference between the two? That's going to be nickel. Well, it's going to be plus 2 itself. So we've got nickel, and then it's going to be 2 plus. Looking at the next one, coordination number, I've got 1, 2, 3, 4 dative covalent bonds, so it's going to be 4. The formula is nickel, and then of course I've got in this case 4 lots of cyanide, square brackets to show the complex, 2 minus overall. The shape is going to be square, and then it's going to be planar itself. Planar because it's fat, and then square because it's just a square shape, isn't it? So yeah, moving on to the next one, feel free to pause the video and have a go at the following question. Resume once you're ready to go over the answers. So yeah, looking at this one then, of course, I've got here a bidentate ligand, because if I just chop it there, I end up with the rest of the structure being attached over here. So again, I would have to chop it twice because I've got 2 dative covalent bonds. The actual formula of the ligand, if you look at skeletal formula, if I were to just draw the rest of it out from what I can see, I've got NH2 there, and then I've got NH2 over here as well. If I were to draw out the actual structural formula though, I would end up with the following, where I've got NH2 but flipped backwards, so I end up with H2M, and then CH2, and then CH2. So we're just converting skeletal to, of course, in this case, it's going to be structural formula. Is a ligand monodentate, bidentate? Well, we know, of course, it's going to be bidentate in this case. If you were to look at the formula of the central metal ion, well, we know all of these actual ethane 1,2-diamine ligands are going to be, of course, neutral. So cobalt is going to be the same as the actual charge of the complex itself. So we've got cobalt 3 plus. The coordination number is still going to be 6, and that's why it has a octahedral shape still. So the shape is still going to be octahedral itself, but of course the formula now is a bit difficult to actually write out. We would end up with cobalt, and then of course I'm going to end up with 3 lots of H2 and CH2, CH2, and then NH2 itself, and so I end up with a square bracket around all of this. Don't forget the 3 over here, and then it's going to be 3 plus overall. Now you could have shorted that down, because in some cases the examiner accepts EN instead, so you could have had cobalt and then EN, because that's quite a mouthful to write out, 3 lots and then square brackets like this, and then 3 plus itself as well, and there is that one done. Moving on to the final one, feel free to pause the video again, have a go at the following, and then resume once you're ready to go over the answers. So looking at this one then, right, we can clearly see we've got ethane dioic ions, the one that we need to remember, just like ethane 1,2-diamine. We chop it here and there, and we're left with the following structure, which of course, if we were to rewrite that out, we would end up with something that looks like this, similar to ethane dioic acid, but remember it's got negative charges on there. If we were to actually write out the actual formula of the ligand, we could put C2O4, and remember it's going to be 2 minus overall as well. Is the ligand going to be monodentate or bidentate in this case? Well, we would say, because it forms 2 dative covalent bonds, it's going to be bidentate itself. The actual formula of the ion, well, ion over here, right, that's our atom that we're dealing with, turning it into an ion. We've got 3 minus overall. We've got 3 lots of these ligands over here, so it's going to be, of course, 6 minus, and 6 minus, 3 minus, what's the difference? It must be ion 3 plus itself. What about the coordination number? Well, that's still going to be 6, because you've got 6 dative covalent bonds, where 2 of them come from, of course, 1 ligand, but you've got 3 ligands overall. The formula and the shape of the complex ion is still going to be octahedral in this case, and of course we end up with the formula being iron, and then of course we've got 3 lots of C2O4, and then the complex ion, which of course is going to have a charge of 3 minus itself.